Alright, hello everyone. This is Mr. Smith, and we are going to run through electricity, the basics. So last week we talked about resistance, at least introduced resistance and what that meant, and we'll come back to it again in this PowerPoint. But mainly what we're going to talk about are the other parts of an electric circuit as well. Now we're not going to talk about what an electric circuit will really look like, or the design of an electric circuit. That's for another lesson. But today we're going to talk about voltage, resistance, as well, current and power as well. And of course, how to calculate power using voltage and current, and how to calculate resistance using voltage and current. So, of course, a quick review on atoms. All material are made up of atoms, protons, electrons, and neutrons. Of course, the protons and neutrons, which are contained in the nucleus, do not move. It is those electrons that actually flow and create electricity. Now, if you consider different types of materials that made really, or that gathered static electricity really well, were insulators, whereas conductors allow electricity to flow very well. So electrons flow through conductors really easily. They do not flow in insulators at all. In fact, they get stuck and just stay in place. And then semiconductors are somewhere in between a conductor and an insulator. They do allow electrons to flow, but not as quickly as a conductor allows electrons to flow. So semiconductors can be incredibly useful in different scenarios, especially for like capacitors, which are used in electricity a lot. So resistance. Resistance, we already learned last week. It is the difficulty in which current passes through a circuit. What is resisting the electrons? We also called it the friction of electricity. So the higher the value of resistance, the harder it is for those electrons to flow. We measure that in ohms, which is often represented with this omega sign. And when you see resistors in a circuit, they may be represented as a squiggly line or as a box like this. Typically, when you have a box like this, you'll see the resistance value placed inside of it. So, conventional current versus electron current. So, we know electricity, or current electricity, to be the flow of electrons. Now, electrons flow from the negative side to the positive side. So if this were a battery here, these little short and long lines, electrons flow away from the battery, away from the negative side of the battery, into the positive side. That's electron flow. However, conventional current, this was before we understood electrons, was deemed to flow from positive to negative. So people thought that the positive charge was flowing into the negative side. And so this is often still used when people are talking about electricity flow. It's called conventional current. So basically, if you're talking about the flow of electrons, electrons flow from the negative side to the positive side, but the direction of current is considered to go from positive to negative. So that's very important to distinguish. Electrons actually flow from negative to positive, just like they like charges repel, so they're trying to get away from that negative side to the positive side. But the direction current flows is actually opposite of that. It's going from positive to negative. That's very important. So if you think about current mathematically, now we won't actually use this formula right here. Current equals charge, Q, divided by time. But it does help understand, it helps us understand what electric current is. So electric current is the change at which charge travels around a current or a circuit. So Q is the charge of an electron, and T is the time that charge is passing. So current is how fast that charge is moving within a circuit. So amps, or 1 amp, is 1 coulomb, or 1 charge, passing a point in a second. It is basically the speed of the electrons flowing through the current, or the circuit. So once again, we won't be using this formula in our calculations, but it does help us understand what current is. Now there are 2 different types of electric current. There is DC voltage, or direct current, and there's AC voltage, which is called alternating current. DC current is often what you have, the type of current that would be in a battery, or your phone would experience DC current. Normal batteries hooked up to a circuit is just direct current. Alternating current is the type of current that comes from the wall, or your electric sockets. This is a changing current, which is much more dangerous than direct current. And we also won't be getting into this very much. Alternating current becomes more complex. Direct current is much more easier to understand and is more useful to us in the end. So if you were to zoom in on an electric circuit and look at the wire and look at the electrons within that wire, we can take a look at how they're actually behaving when we talk about the flow of electricity or current. So normally electrons are just moving around in random directions. They have no specific direction because there's no specific charge pushing them. And so you can see these guys, these little green dots are electrons, of course, and they're just going in any sort of direction. This is called constant motion, or constant thermal motion, because everything has heat. Now when a potential difference is introduced, so that would be hooking a battery up to a circuit. The battery has a positive side and a negative side, so you have 2 different potential energies there, the positive and the negative, and that creates an electric circuit. So when an electric circuit is introduced, an electric field is also produced, and that electric field will actually push on these electrons. The electrons feel that electric field, and they start to accelerate in a specific direction. See how they're all kind of pointed in this direction because that's the direction of the electric field. So this red line represents the electric field, and of course they're all pushed in that direction, or they feel that electric field. So they start to move in that direction. And as they're moving through the electric field, they actually bump into other particles. The whole wire is made up of atoms, and so depending on what it's made out of, they bump into them more quickly, and they slow down due to those other particles. So this is where that conductor or insulator comes into play. Conductors allow these electrons to flow quicker through the current, whereas insulators kind of push back a lot more. They have a lot more resistance to those those electrons. So depending on what the wire is made out of, you can have a different amount of resistance within the wire. So you can imagine these people, they're really crowded on the wire, and they slow down, whereas if there are a lot fewer, they move a lot quicker. That's the same thing with electrons. So we just talked about current. Current is measured in amps. Now we're going to talk about voltage, which can be synonymous with electrical potential energy. Now we talked about potential energy last semester when we talked about mechanical potential energy. The potential energy of something being high up, so that was gravitational potential energy. You could also have elastic potential energy, where you compressed a spring and that energy was stored inside of the spring. Well, you can also have electrical potential energy, where there is a difference in the amount of charge in a certain place. For instance, a battery. A battery has two sections, and so there is a potential energy within the battery that you can measure. Now, this is measured in voltage. So electrons, of course, are pushed away from the negative side, and they flow into the positive side of the battery, like we saw in the current section earlier. And depending on the difference between that negative charge and that positive charge, the electrons will flow at a different rate. So that difference between the positive and the negative side is the voltage. That is called electrical potential energy difference. That is the definition of voltage. So as electrons move away from the negative terminal, their potential energy is converted into different things. So this is often seen as heat. This is why your batteries and your phone start to heat up drastically. But this can also be light. So your computer screen or your phone screen produces light during that flow of electrons. The electrons flow through and they produce light, depending on what they go through, and they produce heat or sound. Now, of course, a circuit can mean thousands of different things. So the voltage is that difference in the potential energy between 2 points. So your battery has a positive and a negative side, and the difference between those two, the difference in their potential energies, is the voltage. So a mathematical representation of voltage, just like we did with current, voltage can be described as the voltage drop that occurs when 1 coulomb of charge transforms 1 joule of energy. Basically what that's saying is voltage is how much energy it takes to move electrons from one place to another. So those electrons move from the negative side to the positive side, and the voltage is how much energy it takes to move those electrons from positive to negative. How much energy it takes to move them is the voltage. Now, once again, we're not going to be using this formula in our calculations, but it is good to understand mathematically how voltage is developed. So we measure voltage using a voltmeter. Sometimes they'll look like this old analog, or sometimes you'll see these digital versions. Oftentimes you'll see these things called multimeters, which can measure a bunch of different things all at once. They often have voltmeters integrated into them. So a voltmeter is actually hooked up to a circuit in parallel. Now, we haven't really talked about what parallel versus series means, but if this is your circuit, the voltmeter doesn't have to be connected through the circuit. The voltmeter can actually just be placed between or on top of the circuit, and it can actually measure the voltage going across something without actually having to be a part of it. This will make sense more later when we actually start building circuits in FET simulation. But for now, just understand that in order to measure voltage, it doesn't have to be connected directly into the circuit. Whereas current, measured with an ammeter, does actually have to be integrated into the circuit in order to measure current. So current, once again, is measured in amps, and you can use, this is a basic ammeter. Very simple. So if you imagine we have the ammeter hooked up right here. Now this side is the negative side, and it's hooked in directly, and so that current goes through the device back from the positive side. And so we know electrons are actually flowing from the negative side of a battery through the device and then back into the circuit through here. This setup right here is the exact same thing shown on the right. So here is your battery, here is your ammeter, and here is your resistor. And so this is hooked directly into the circuit. This is called series. So when it's hooked up directly into it, then you can actually read the current. Whereas, like I said earlier, a voltmeter doesn't have to actually be within the circuit. It can measure across an object in the circuit. So this setup right here is the exact same thing. Here you can see you have a full circuit here, and then you take the voltmeter and you hook it onto the circuit from the outside. You don't actually have to disturb your circuit. So Ohm's Law is a calculation that we use in order to determine the resistance of a certain substance or a material if we understand the voltage and the current that's running through the circuit. So if we have a resistor and we want to know the resistance of that resistor, we first have to know how much voltage is running or is connected to the circuit, and then we also have to know how much current is flowing through the circuit. If we know voltage and current, we can find the resistance of a material. Now you can rearrange this formula in 3 different ways. Sometimes you'll see this triangle being used. It is useful. I'm not particularly a big fan of it. It's here if you guys want to try and use it, but personally I use these 3 formulas instead and rearrange them whenever I need. So if this is Ohm's law, resistance equals voltage divided by current. Here we can bring voltage to the other side, or I'm sorry, current to the other side. So we multiply both sides by current, and then we have voltage equals current times resistance. Or what we can do is we can multiply both sides by current, divide both sides by resistance, and then, multiply both sides by current, divide both sides by resistance, and then you get this guy. Current equals voltage divided by resistance. So there are 3 different ways you can rearrange the same formula. So Ohm's law is basically telling us that the greater the resistance of a material, the less current can flow given a specific potential difference. So what that means is if this resistance is really high, then our current is going to be really low. But the lower our resistance is, the higher our current becomes. So here is a little practice for you. If we want to know the current flowing through this circuit, we have 30 volts of power coming through here, and we have 10 kiloohms. So this is also known as 10,000 ohms. So imagine that we have 30 volts and a 10,000 ohm resistor, also known as 10 kiloohms. We can calculate the current flowing through by dividing 30 volts by 10,000 ohms. And that would give us 0.003 amps. Now, we simplified this into 3 milliamps, but in reality, we know this equals 0.003 amps. So, in order to find the current flowing through here, all we did is we went and used this formula right here. Current equals voltage divided by resistance. We said, we have the voltage of 30 volts, and we divided it by 10,000 ohms, and we got 0.003 amps. Now if we want to find resistance, because we have the voltage and the current, then all we have to do is plug it into this guy right here. Resistance is voltage divided by current. So all we have to do is say 9 volts divided by 2 amps, and that will give us 4.5 ohms. So no matter which way, or no matter what two pieces of information you have, whether it's current and voltage or current and resistance, you can find the other part of the formula. Finally, let's talk about the last thing, and that's power. So the power delivered by a circuit. So power is the rate of which work is done in the circuit. So we didn't really get to touch on power last semester, but you can measure power in mechanical potential energy just like you can in electrical potential energy, or electrical work done. Work, of course, is the change in energy. Here, we're changing energy into different things, such as a light bulb is turning electrical energy into light. We can measure the power or the rate that that energy is being converted if we understand the voltage and the current that's running through the circuit. So, here is a basic understanding of power, which is the amount of energy or the amount of work done divided by the time. So basically, how is your work changing as time passes? Well, this can actually be translated directly into power equaling voltage times current. So if we know the voltage, we can multiply that by the current in the circuit, and that is how much power is being delivered by a circuit. So let's do an example of that. If we have 0.5 amps of current flowing through a circuit, and we have it attached to a 9-volt battery or a 9-volt power source, then all we have to do is multiply 9 volts by 0.5 amps, and we get 4.5 watts. So our power equaled 9 amps times 9 volts multiplied by 0.5 amps, and that gave us 4.5 watts of power. Of course, if you have the wattage or the power and you have the volts or the voltage in the circuit, we can actually backtrack to our current instead. So all we have to do is rearrange this formula here. Our power equals voltage times current, and if we want current instead, well, we just take our voltage to the other side by dividing both sides by voltage. You divide power by voltage, you have P over V, and you're just left with I on the other side, hence this formula. Then, of course, we plug in our knowns, which is 80 watts divided by 120 volts, and that will give us about 0.667 amps. You can also represent that as 667 milliamps. So that's pretty much all I have for you today. That was just a short lesson on voltage, current, and power, as well as Ohm's Law.